In this video, we're going to look at the conversion of an alcohol to an alkyl halide. So we know at this point that an OH group on its own is a poor leaving group, and there's a couple different ways that we can make it a better leaving group, but what we're going to be doing under these circumstances is using acidic conditions, in which case we can protonate it to make water, which of course is a good leaving group. Water is positively charged when it's attached to something else, and when it leaves it becomes neutral, and that makes it a good leaving group. So, as an example, we can use this alcohol. I'll use ethanol. I'm going to put it in solution with hydrobromic acid, so I have acidic conditions, and I will end up with ethyl bromide. So, in this reaction, my first step is going to be the protonation of the alcohol to make a good leaving group. It's an acid-base reaction, so I'm using equilibrium arrows. Now I've got a positively charged water. Now this is a primary carbon, and so I'm not going to see a carbocation at the primary center. What I've done in solution here is I've kicked off this Br- when I protonated my alcohol. This Br- is my nucleophile. It's going to come in and attack that carbon as my leaving group leaves, and that will bring me over here to my alkyl bromide right there. So this, as we hopefully are familiar with at this point, is a SN2 reaction. It's concerted in that rate determining step. The nucleophile attacks as the leaving group leaves. And that's because we have a primary system. It's unhindered. There is plenty of room for the nucleophile to come in as the leaving group leaves, and it avoids the very unstable primary carbocation intermediate. So I could also start with a more hindered system. In this case, I'm going to start with tert-butyl alcohol. I'm going to put in solution HBr again. And in this case, again, I'm going to get an alkyl bromide. This is tert-butyl bromide specifically because of the starting material that I used. In this case, I'm going to draw my little bond in there. Same first step. I've got a poor leaving group. I want it to go, and so I'm going to have to protonate it. That gives me this protonated species. Now in a tertiary system, it's going to be too crowded for the leaving group to leave as the nucleophile comes in. So this leaving group leaves, and this is my rate determining step. It gives me a carbocation intermediate here, and then the bromine that was kicked off can come in and attack, and that gives me my alkyl bromide at the end. So this, of course, will be an SN1 reaction. The rate determining step is the leaving group leaving, and so that's what's going to hinder the reaction in terms of its rate. And so the product is the same whether I use a primary or a tertiary system, but the mechanism is different. If you have, to begin with, a secondary alcohol, it can go either SN1 or SN2. It just depends on what the substrate looks like, how bulky it is. So there's not really a way for us to predict that. What we would have to do is look at the products and have an idea. If we had started with a chiral starting material, then we would see stereospecificity in an SN2 reaction, whereas in an SN1 reaction, we would have a racemic mixture. And so that's one way that we could tell by looking at the products, but in order for that to happen, we would of course have to have a chiral starting material. If we want to go from an alcohol to specifically an alkyl chloride, we often add something that we call the Lucas reagent, and that is adding some zinc dichloride. And this is sort of an activator for this reaction. Cl- is a weaker nucleophile than bromine because it's smaller and it's less polarizable. So the zinc dichloride in there can really help activate this reaction and get it to go at a quicker rate. So in this reaction, I'm going to start with my alcohol. What I do is I put in solution my zinc dichloride and HCl. And what can happen is the oxygen can attach onto that zinc fairly easily. And when it does that, I get this intermediate species. The zinc is negative because it was neutral and it's accepted electrons. The oxygen is now positive because it's donated electrons. And what it really comes down to is that this is a really good leaving group. And so because it is such a good leaving group, it increases the rate of the reaction, because in order for the substitution to occur, the leaving group has to leave. So this zinc chloride serves to make a really good leaving group, even a better leaving group than water. And so what we see happen is this guy leave. Let me change colors here so we have a little bit better picture of what's going on. So I'm going to draw the arrow swooping away, and so that's going to give me a carbocation. This is a secondary system. We've said before they can kind of go either way, but in this case, because of that really good leaving group, it's going to give me a secondary carbocation. Now remember that HCl is a strong acid, so it's going to dissociate to an appreciable amount in solution, meaning that we will have chloride ions, which also will serve as the nucleophile in solution. That can come in and attack, and I will end up with my alkyl chloride in this case. And then as a byproduct, I have the zinc, which has the OH attached to it, and then two Cl2s. So it's going to be still negative, but the oxygen is going to be neutral now. In this case, a primary system will go SN2, again to avoid that primary carbocation. Secondary and tertiary will go SN1. This zinc oxide looks kind of funny, so the zinc is attached to the oxygen and also attached to the two Cl2s. So although we can accomplish the transformation from an alcohol to an alkyl halide using these methodologies, there are some issues. First is that the primary and the secondary systems go slower. Again, in order for a substitution to occur, we're going to be dependent on the leaving group leaving. And the leaving group is less likely to leave a less substituted carbon. Secondly, if we want to add heat to the system in an effort to get it to go, we risk elimination products and dehydration. So instead of getting the desired substitution product, we end up seeing an elimination product. And then, of course, because tertiary and some secondary systems can go through the SN1 mechanism, we can see rearrangements, which can lead to a mixture of products. So the rate can be problematic when we're talking about the primary and the secondary systems, and then these last two would have to do with a mixture of products, which then we have to purify. Not only do we not get the desired amount that we want, but we have purification issues to isolate the desired compound.